Hello, and welcome to this short video demonstrating host-to-embedded controller data enablement. My name is Matteo Tullo, and I am a software engineer on Microsoft's Windows Silicon and System Integration Platform Firmware and Drivers team. I am part of the Open Device Partnership, or ODP, effort to enable secure, reliable, and reusable firmware on computing devices. Okay, so let's start with a quick overview of the data pipeline to discuss, at a high level, what will be demoed. Okay, so here's a simplified diagram of the data path a request and a response will take through the system. The EL0, EL1, and EL2 labels refer to exception levels in ARM trust zone, which are basically privilege levels for code execution. The device I'll be demonstrating on uses an ARM-based CPU, and so that's why I use this nomenclature. It's also worth mentioning that if you are using a different architecture, say x86, this will also be supported. However, it doesn't exactly follow the data flow below. You would just need an OS driver that can communicate between your OS and your EC over the hardware bus. The ACPI request can then be sent directly through that OS driver over a non-secure transport, such as eSPI on x86. Okay, but back to our platform. So firstly, a user mode level 2E, or TUI, or terminal user interface app will make a request for data, like battery voltage or temperature sensor data. The request will then percolate through the operating system, traveling across exception levels until it gets to the secure world, where a hardware bus capable of talking to the EC lives. That request is then dispatched over the hardware bus, and the EC receives the request, decodes it, and queries the real data, and then it sends a response. That response then travels back the same way it came, but in reverse, eventually percolating up to the terminal user interface app, and then that data gets visualized. Now, let's see that demo in action. Welcome back. So here I have a demo device that I have remote desktoped into. This device is running the demonstration TUI app, calling ACPI functions via an ODP kernel mode driver, and the EC is running all open source ODP EC firmware. The TUI app, the kernel mode driver, the secure partition code, and the EC firmware code is all open source and can be found on ODP's GitHub repos. Okay, so let's start the app. Okay, so right off the bat, we can see that the app has tabs for different data sources. These tabs update in the background with real-time data, and when we switch to these tabs, we see the data visualized in a pleasing manner. The first tab is a tab for debug data directly from the EC. This is an incredibly useful tool for checking logs from the EC. In order to decode the messages from the EC, you need to attach an ELF file of the EC firmware running on the device to get the debug symbols. Here we have real messages coming through the EC to show what messages will look like. This is very simple. You just need to attach the ELF file. In this case, it's called Monarch. Attach Monarch. And we can see some messages coming in. These are all live messages coming directly from the EC. Cool. So let's move on to the next tab, the battery tab. So here we see that static information is listed on the left, along with dynamic data being updated once a second on the right. Currently, we see that the battery is discharging at a rate of about 3 amps. The current voltage on the battery is just shy of 11 volts. A capacity versus time graph is also plotted, so we can see how the capacity changes over time. There is also a spot to set a battery trip point, where the EC can generate an interrupt to the app that the threshold has been passed. Now let me plug in a charger to the device, and we should be able to see the battery state go from discharging to charging. A big battery symbol here on the right should also let us know that we are charging. And there we go. We have a nice visual indicator that shows up, and then we can see that we are charging at a rate of just around 5 amps. Okay, so the final tab we will look at in this demo is the thermal tab. So here we can see two graphs, one graph of temperature versus time, and another graph of fan RPM versus time. You can see the live temperature on the bottom left, as well as thresholds and fan state levels. The fan state levels indicate at what temperature the fans turn on, at what temperature the fans start ramping up, and at what temperature the fans are maxed out. You can even set the fan RPM manually through this box right here. We can see that after we plug in the charger, the temperature has started to slowly rise, and as such, the fan RPM has started to increase, which is pretty cool. Let's try manually setting the fan RPM to a lower value, say 1000. Cool. We can see the data update. And we should see that the temperature starts rising even more now that the fans are not running at a high enough speed. So all this data that's being queried in the TUI app follows that same data path I discussed earlier. All the data is real data being queried in real time by the embedded controller. Thus, we can see that data can be accessed from the EC in a secure and reliable manner. Welcome back. Finally, let's take a deeper dive into the data flow from the host operating system to the EC and back. Okay, so when the TUI app executes a data request, the data request gets forwarded to the ODP kernel mode driver, and the kernel mode driver then dispatches that request to the Windows ACPI driver. The ACPI driver wraps the request up in an ARM FFA call and sends it up an exception level to the hypervisor, Hyper-V. Hyper-V then forwards that message up another exception level to the trusted monitor. It is here where the message passes from the normal world to the secure world. The message gets passed to Hafnium, which is a secure partition manager. Think like hypervisor, but in the secure world. Finally, the request reaches the HAF EC service, which is an ODP service that is basically like the arbiter of the hardware bus. In our demo, the hardware bus that we used is eSPI, but in the future, we at ODP plan to support more hardware buses, like, for example, I3C. The hardware bus is connected to the EC, and thus the data leaves the host. We at ODP are also working to encrypt the EC channel in a manner that will slide really easily into the current design to ensure that we are operating at the highest caliber of security. Okay, so now let's look at the secure EC side. The data comes in over the hardware bus. For the demo, specifically as an eSPI out of band or OOB message. The host service, in this example called the eSPI service, releases the hardware bus, decodes the message, and forwards the request to the appropriate subsystem within the EC using our ODP IPC that's part of our like EC suite of firmware tools. If a battery request is received, for example, that request gets forwarded to the battery subsystem. Whatever subsystem the request is meant to go to is responsible for handling that request and responding with data, whether that's data that's been cached from startup, for example, or dynamically collected at request time. The subsystem then builds a response packet and sends it back to the host service with the data, where the host service will then initiate a transaction on the hardware bus. The whole dance is basically done in reverse now as the data travels through the host to the operating system. Okay, so here is a more detailed sequence diagram visualizing a path that the packet takes. I'm not going to discuss it because I basically just did that, but feel free to pause and look at to get a more detailed example of the data path that the packet will take. Cool, and that's it. Thank you so much for watching and learning a bit more about how the host talks to the EC. If you'd like to learn more or inspect any of the source code, please check out our GitHub page. If you have any questions, also, please feel free to ask in our publicly facing Zulip channel or our public Discord server. Thank you again for watching, and keep building secure code.